Okay, so let's talk about the normal distribution. Before we start, let's quickly just go over the concept of normally distributed data. Now, in nature, the tendency for data to clump together is pretty rampant. I'll give you a short example of what I mean. Let's say we have some set S of ages of retirement represented by continuous random variables x1 through xn, so some small sample of ages, where our random variable can assume the ages of anywhere between 40 as our minimum and 100. Recall the ages at which the individuals around you have retired. Most of them have certainly retired between the ages of 40 and 100, but the majority have certainly retired directly in between 40 and 100, around ages of 60, 65, let's say 70. You certainly won't be seeing many retirees below the age of 40 or almost any above the age of 100. This particular set of continuous data can be perfectly modeled by a normal distribution model. The normal distribution is above all a notion that describes a particular relationship that may exist between the values of a given data set. For any data set to be considered normally distributed, the data set must abide by two rules. The first rule requires that all measures of central tendency, which are the mean, the mode, and the median, be equal. So the mean equals the mode equals the median. The second rule is known as the empirical rule. And the empirical rule says that 99.7% of all of the data set must be found within 3 standard deviations above and below the mean. We'll see what that means in just a little bit. All data sets that follow the rules of central tendency and the empirical rule are said to be normally distributed. So, normal distribution. And normal distributions can be visualized via a bell-shaped curve. Whenever we have normally distributed data, we can use this bell-shaped curve to model such data visually. So what are some properties of our visual model, our bell-shaped curve? Well, the first and most noticeable property is its symmetry. The bell-shaped curve is perfectly, theoretically, perfectly symmetric. Splitting the curve directly into two halves, two 50% halves, the lower 50% and the upper 50%, as we can see here. This symmetry is a direct result of the fulfillment of our two main criteria, fulfillment of our two main rules. If our two rules were not to be met, then our distribution graph would be skewed. Coming back to our non-skewed, symmetrical, bell-shaped curve, our normal distribution, line of symmetry is a representation of our first rule. Mean equals mode equals, let's put it here, median. The height of our bell-shaped curve corresponds to the mode, the most commonly occurring value in our data set. The spread of our bell-shaped curve is directly related to sigma, our standard deviation, which plays an auxiliary role also in determining the height of the graph as well, but the mode plays a much bigger role in that. The median is the dead center value of the graph. The only thing that could skew our graph to the left or to the right would be an imbalance or an inequality between the mean and the median, or the mode, of course. The mean is that parameter that could shift or skew the graph left or right and change it from normal drastically, because it is most influenced by outliers of all three central tendency parameters. Let's visit the empirical rule in a little bit more detail. Referring back to our set of retirement ages, we can establish that mu is 40 on average plus 100 divided by 2. This value equaling 70. Since we need to fulfill mu equals mode equals median, we're going to make it to 70. And we label the center. We label our axes with 40 to the left and 100 to the right, and dead center 70. Let's say the standard deviation, sigma, is 2 years. We split our graph into 3 standard deviations of 2 years each in both directions. A negative 2, 3, 2, 3. This graph now tells us that at 1 standard deviation away from the mean, our values 72, and at 2 standard deviations away from the mean, our values, age values of 74, and at 3, age values of 76. The reverse holds true for standard deviations in the other direction. 70 minus 2, which is 68. 2 standard deviations down, which is 66, and another 2, so that is 3 standard deviations away from the mean, 64. What this graph automatically can tell us is that not everybody at the age of 64 really wants to go into retirement, which is a good thing for the economy, but I guess a bad thing for health, especially at old age. Okay, so let's try and interpret this graph. So what the empirical rule says is that 1 standard deviation away from the mean will contain exactly 34% of all of the data from our set S. This means within 1 full standard deviation, that is 1 standard deviation minus in the negative direction and another standard deviation in the positive direction, 1 and 1, will yield together 68% of our data from S. The empirical rule also says 2 full standard deviations in both directions will yield 95% of S, while 3 full standard deviations will yield 99.7%, which is almost the entire set. The key here is that these percentages are equal and they are constant for all normally distributed data sets. So that means for all normally distributed data sets, within the first standard deviation, plus and minus, we will cover 68% of our data from that data set. Within 2 full standard deviations, we will cover 95%. And within 3 full standard deviations, we will cover 99.7%.